previous videos, we defined symmetry as invariance under transformation, and we investigated transformations including reflections, rotations, translations, and glides. In this video, we look at transformations that involve a change of scale, a subject so fascinating that it deserves a video all on its own. Welcome to the weird and wonderful world of dilatation symmetry. If we look at these concentric circles, we discover that we can map the structure onto itself by increasing the size of all the circles. This is dilatation symmetry. The structure is invariant under the operation of dilation or dilatation. The same applies to this set of rectangles. It remains invariant under a change of scale. How does this work? Well, in these two examples, the dilatation symmetry is based on this familiar series of numbers, the Fibonacci series. I'm sure you're familiar with this series, which is produced by adding any two numbers to produce the next one. 3 plus 5 is 8, 34 plus 55 is 89, and so on. This series has many fascinating properties, one of which is the fact that the ratio between any pair of numbers in the series approximates 0.62. It doesn't work so well at the bottom of the series. 1 divided by 2 is 0.5, 2 divided by 3 is 0.66, and so on. But once we get to 8 divided by 13, it approximates to 0.62, and to 2 decimal places, this approximation remains no matter how far we go up the Fibonacci series. This ratio is so important that it's given a name. It's called the golden ratio. The dilatation symmetry of this structure exists because their diameters are based on the ratios of the Fibonacci series. I've cheated a little bit with the smaller circles to make it work, but essentially the diameter of each circle increases according to the Fibonacci series. The golden ratio is not the only way to produce dilatation symmetry. Any ratio will work. In this example, the diameter of each circle is double the diameter of the circle inside, and once again we have invariance under dilatation. If we return to our original circle, we see the first of many amazing properties of this circle. If we place dots, quarter turns around each successive circle, and then draw a line, we produce this structure. That's interesting, but it becomes much more interesting if we turn it into a spiral that looks like this. This spiral also has dilatational symmetry. Here are two spirals, and we can see that if we dilate one spiral, it will map onto the other. This is dilatation symmetry. It turns out that this spiral is one of the most important structures in the universe. We see it in heavenly bodies, we see it in weather patterns, we see it in the arrangement of seeds in a sunflower. To demonstrate this dilatation symmetry, we can take a copy of the curve, increase its scale, and find that it maps onto itself. We can see that it can be then placed perfectly onto our sunflower. The rectangles that we saw earlier are also based on the Fibonacci series. In this case, it is the dimensions of each rectangle that increase according to the numbers in the series. This series has fascinated designers, architects, and artists for centuries. In fact, we even all carry a copy of it in our pockets. We can see these ratios and these proportions in this logo. If we place the logo inside the largest square and make a circle, then draw another circle inside the square next to it, we find that this smaller circle fits perfectly into the curve of the blue wave. There's another way to draw this set of rectangles, and it goes like this. With our rectangles arranged like this, we see that we can produce a very familiar curve. And here it is, placed on our sunflower. Shells famously have dilatation symmetry. In this shell, we don't see the Fibonacci spiral, but another ratio. Nevertheless, this again is an example of dilatation symmetry. In this familiar logo, we see the golden section at work. Was this done purposely by the logo designer? They say no, and that's a fascinating story in itself. But this logo was consciously made, producing circles related by the golden section. Architects have been fascinated by these ratios. This temple from Sicily, based on the Parthenon in Greece, we see the golden section at work, as we do in many structures in the Taj Mahal. We see the Fibonacci spiral at work in the human body, in art, and in design. A particularly elegant example is this beautiful logo, the NITV logo. NITV is part of the SBS network. The SBS logo started life based on a map of the world and looked like this. Later it was transformed to look like this, and these ellipses are based on circles related by the golden proportion, the golden ratio. In the NITV logo, the black ellipses are based on arcs of circles, but not the coloured structures. These turn out to be, perhaps you guessed it, examples of the Fibonacci spiral. Was this done on purpose? I'm not sure, but we see these proportions in virtually every aspect of the design, including the relationship between text and the logo itself.
Trees are amazing things. They have all sorts of symmetry. If we look at them from the front, we can see that they have more or less mirror symmetry. If we look at them from the top, they have radial symmetry, rotational symmetry. But there's another very interesting symmetry that they have. When it comes Christmas time and I need a Christmas tree, I don't need to buy a whole tree. I can just buy a branch, and all its smaller branches make it look pretty much like a tree. And then if I want to make a model train set, I can just break off a twig from the tree, and again it looks like a tree. At these three different scales, the twig, the branch, the whole tree, it still looks like a tree. So what symmetry is happening here? Well, the symmetry is one of scale. The geometry is the same when we make the structure bigger. This is symmetry of scale, dilatation symmetry, and we can also call it fractal geometry.
A simple example of fractals in geometry can be produced like this. If we take a blue triangle and place a pink triangle upside down inside it, then keep doing that so that there's a pink triangle inside every blue triangle, we get a structure that looks like this. And we could keep doing this forever. If we dilate this structure, we see that it maps onto itself. And this is the basis for all of the structures that we saw at the beginning of this video. Until next time, bye for now.